Alright, so this is a statics problem. This is a problem where we will calculate the moment about a point. It's problem 4.24 in the textbook. And you can see it consists of this pole. And the pole is mounted to the ground at point O, and it's got these cables that are attached to it. So there's this cable CAD that goes through this ring here, and cable DBE that goes through this ring up here at point B. And the force, the tension in cable CAD is 250 newtons, so it's pulling at point A in the direction defined by C, and then at point A in the direction defined by D. And there's another force in cable DBE that's 100 newtons. And the problem asks you to use a vector approach to compute the vector moment of all cable forces about point A, and then the same thing about point O. So this is a pretty straightforward problem, and we'll use this then as an opportunity to not only understand how to calculate the moment about a point, but also to make 3D vector plots, which I think help us visualize these moments a lot better. So you go ahead and work on it and come back, and we'll go through the solution. All right, so yeah, I mean the problem itself isn't very hard. The geometry is completely specified. You have these I guess there's 6 points, O, and then A, B, C, D, and E, and we can put those coordinates in. And once we have those coordinates in, then we have defined the position vectors that define the directions of the forces. So the position vector RAC, RAD, and then RBE and RBD. And so we know the directions of the forces, and we know the magnitudes of the forces, and it's a pretty straightforward thing then to calculate the cross product of the position vector that defines the location of the force relative to the point and the force itself, and that gives you the moments, which are vectors. So we'll do that, and then we'll also visualize these moments, which I think is really nice because it lets us kind of understand what the moment vector really means. So here's the ease program. So the first thing I'm going to do is enter the coordinates of all of these points in millimeters. So this is pretty easy. These points are all defined as vector variables because they have 3 coordinates, and I'll just go through one by one and enter these. And then I also enter the magnitude of the 2 forces, so 250 newtons and 100 newtons. And once those are all in there, it's pretty straightforward to define the position vectors that define the force directions. So these are RBE, RBD, RAD, and RAC. And of course RBE is just point E minus B, and so on for the rest of them. And then finally, let's define the force vectors themselves. So the force is the vector is just the magnitude of the force, and then multiply that by the unit vector in the direction of interest. So for example, for force FBE, it's just the magnitude of the force, which is the tension in that cable, FDEB, and then I'll multiply that by the position vector RBE divided by its magnitude, which is the unit vector. And I'll go ahead and do that for the other 3 forces as well. So the first part of the question asks for the moment about point A, and so to do this, of course, we would just take the cross product of each of these forces with the position vector that goes from point A to the point where the force is applied to the structure. So there are 2 forces that are applied directly at point A, so FAC and FAD. They produce no moment because the position vector is 0 associated with those forces, and therefore the only 2 forces I have to worry about here are FBE and FBD. So the moment vector about point A is RAB, and we'll cross FBE, so that's the moment produced by the force FBE, and then I'll add to that RAB cross FBD, so that's the additional moment produced by force FBD. And RAB is just point B minus A. So here's those calculations. And if I solve, I see that the moment vector is what, minus 7,200, 7,200, 0, and the units of that are Newton millimeters. So here's where I think it's nice to actually build a 3D plot, and we will do this using the VectorPlot directive. So this is a nice opportunity to explore the use of that directive. So in this directive, I first of all have to give a name. So I'm just going to call this plot part A, and then I have to list all of the vectors I want to plot, and then following the name of the vector I have to define the origin and the color. So first thing I'm going to do is plot the position vector RAB, so that's the part of the structure that I'm interested in, and then that's going to start at coordinate A, and we'll make that black. And then I'm going to plot the two forces that I'm interested in, so FBE, and I'm going to start that force. The origin will be point B because that's where it's applied, and we'll make that force red. And the same thing for FBD, so it's applied at point B, and it's also red. And the last thing I'm going to do is plot the moment vector. Now the moment vector, if you look at it, is on the order of thousands. That's the magnitude of it, whereas everything else is on the order of 100. So I'm going to scale it. I'll just divide it by 100 and make a new vector that's just the moment vector divided by 100. I'll call that MA scaled, just so that it appears on the plot and doesn't make it so big that everything else is basically not visible. So the last vector I'm going to include in my VectorPlot directive here is MA scaled. I want that to be applied at point A because that's the point we're taking the moment around, and let's just make that purple. So at this point I should be able to solve, and part of the solution then will go through and build that vector plot. And you can see here, yeah, here's the structure RAB, and then these are these two forces, and you can see they're tending to twist the structure right around that moment, right? So that's what the moment is. It's the axis that the structure is being twisted around. And I think this makes it a little more physical what these moments mean. All right, so let's do the last part, so part B of the problem. And I'm going to go ahead and build a new tab. So I'll just add a tab, and we'll label this tab part B. And most of these equations are common to both parts. I'm just going to copy the equations I have here that are relevant for part B and plop them into a tab labeled part B. I could also use a $include or $insert tab directive, sorry, to include those equations without having to retype them, but I'll do it this way. And now I need to calculate the moment about point O. So here, every one of these forces, all four of them, contribute to a moment about point O, and that moment then is, let's see, ROB cross FBE, and then ROB cross FBD. So that's the two moments exerted by the forces that are applied at point B, and then I also have moments exerted by the forces that are applied at point A, and those would be ROA cross FAD and ROA cross FAC. And I have to define these two position vectors. ROB is B minus O, and ROA is A minus O. And so here are the equations in these to calculate that. And this leads to a moment of 0, and then a 29,647 and 0. So the moment is completely about the y-axis there, and you can again relatively easily build a vector plot that visualizes this. So again, I'll use the VectorPlot directive. I'll call this plot part B, Now I'm going to plot the entire structure, so ROB, and I'll start that at O and make it black. And I'm going to add to this plot all 4 of the forces. So FBE, that's applied at point B, and it'll be red. FBD is applied at point B, and it's also red. FAD will be applied at point A, also red. And FAC will be applied at point A and red. And then finally, I'm going to plot MO. Again, I got to scale it because you can see it's so much bigger than the other ones. So MO scaled, and that'll be applied at point O, and it'll be purple. And here's the vector plot, and it's kind of interesting. You can see that the net result of all of these moments is to try to rotate this pole around the y-axis, right? So there's moments individually that will try to rotate around the x-axis or the z-axis, but they cancel out, and you end up only rotating this thing around the y-axis. So that's the twisting force that this pole feels down at point O.